In this video, we're going to take a look at Kepler's laws. And as an example of Kepler's laws, we are going to take a look at space navigation. So in this example, we're going to start off with the sun in here. So the sun being 99.5% of all the mass in the entire solar system, its gravity dominates everything. And then out here in blue, we do the Earth's orbit. And then in red, we would do Mars orbit. Okay. Now, Kepler's laws, there are three of them, that's it. They're also observational. So they don't really offer any explanations. Newton's law of gravitation does, for sure. But the orbits are all ellipses. And this was a big clue for Isaac Newton in trying to figure out what's causing this to happen, because an ellipse is a conic section, just like the path of a projectile here on Earth would be a parabola. So those are both examples of conic sections. So anything that's moving under the influence of gravity is going to execute a path that's a conic section. And there are three different kinds of conic sections. There are parabolas and ellipses, of which a circle is a special case, and then a hyperbola. And that's an interesting one too, because if we had an object enter our solar system but have enough speed to not get trapped in the sun's gravity, it's still going to get diverted. And so that would come in like this and then escape outward like that. All right, so conic sections, law of equal areas, another clue for Isaac Newton. This says a radius vector sweeps out equal amounts of area and equal amounts of time, which leads to the conclusion that in an elliptical orbit, when an object is closer to the sun, it needs to go faster. And then the law of ratios. So the law of ratios says if you can compare any two objects together, TA, the period of one planet, the period of another, and square it, then that's equal to the ratio of their area, their orbits, like that. So that's our law of ratios. Now we can take these two as an example, and I'm just going to rewrite these really quick because it's much more convenient to use an alternative unit called astronomical units, and we can use any units we want because these are just ratios, and the units are going to cancel. So we define 1.00 astronomical units as being the Earth's sun distance on the average. And so in order to figure out how many astronomical units Mars is away, then I'm going to divide Earth's distance into Mars distance. So, and they're both 10 to the 11th, excuse me, so I don't really have to do that. I can just do 2.279 divided by 1.496. Okay, so that's 1.52 astronomical units. So in this case, Earth is going to be B and Mars will be A, and we'll plug our numbers in here. So we know the distances now, and we know the period for the Earth is 1 year, but let's find out the period for Mars. Great, as we plug in numbers then, we'll let A be Mars. So I don't know what this is. That's still a question mark. But the period for Earth is 1 year. And that's squared. And then the distance for Mars, I can use an astronomical units from 1.52 astronomical units and divided by Earth, which is just 1 astronomical unit. Great. So this is what I'm looking for. And this is 1. So the units that I get here are going to come out to be years. So TA squared is equal to, and then we'll cube this. So 1.52 to the third power is 3.54. And then I'll take the square root of both sides. And I get 1.88. Years. Right, so it takes almost twice as long for Mars to go all the way around in its orbit than the Earth does. So Mars is one of the closest planets to us, but it's actually kind of hard to get to, surprisingly, because we have to remember that if we're going to go from Earth's orbit out to Mars orbit, we can't just hit the gas. Getting fuel off this planet is really hard. And so we want to use the least amount of fuel as possible. So that means we're going to have to coast under the influence of the sun's gravity. So there's a classic video that shows this in a simulation. And I'm going to share it with you right now. And in this diagram so far, we have the Earth, the blue planet, and then we have Mars out here. So we're going to go ahead and play this. And so we give a kick in velocity so that our satellite or our space probe is now in an elliptical orbit around the sun. So the sun's gravity is bending its path, just like if you wanted up a piece of paper and threw it into the recycling bin, just like gravity would bend that path into a parabola. And then when we get to the furthest point, then you can see there's another boost in velocity that happens. So that now we would be in a circular orbit that corresponds with Mars's orbit. And so now we have traveled from one place to another. So yeah, I'm just going to stop that and we'll stop sharing. Great. So that's the period for Mars. And now let's take a look at going to Mars. So in going to Mars, we're going to take an elliptical path, and let's see if I can sketch this out. And so here's an elliptical orbit that at its nearest distance, it matches up with Earth, and at its furthest distance, it matches up with Mars. So the R that we're going to use for this is going to be the average of those two distances. So 1.52 plus 1 divided by 2. And so we'll do that really quickly. And that's our average, so 1.26 astronomical units. And now I can go ahead and plug it into Mars and find out the time it takes for this elliptical orbit, which will be TA, divided by 1 year. So our answer is going to come out to be in years. And we'll set that equal to, so now 1.26 over 1.00, and that's Q. Okay, so our period for this transfer orbit is going to equal 1.26 raised to the third. But when we take the square root, that's the same as raising to a half power. So raising it to the 1.5 power. And here's what it looks like on my calculator. I'm going to take the answer I just got, and I'm going to raise it to the 1.5 power. And so that's 1.414 years. But travel time, we're only going to do half that orbit. That's going to be 1.414 divided by 2. Because we're only going to do half the orbit. And then if we want to multiply that by 12 months, then we get about 8.5 months. Now, the longest interplanetary trip that humans have ever done is traveling from the Earth to the Moon, of course, and that hasn't happened in a long time. As far as people traveling, and so that time was about 4.5 days. 4.5 days out and about 4.5 days back. So if you haven't seen Apollo 13 in a while, that could be a fun watch. But if you think about that, this is a 8.5 month. That's a long time. So hard enough to just go to the moon. 4.5 days stuck in a tiny capsule, like the size of the inside of a Volkswagen, or like probably bigger than that, more like an SUV. So think about that. If you're going to travel somewhere with some friends and you're going to be stuck inside the car for 4.5 days with them, and no showering or anything like that. So yeah, and then 4.5 days back. So that's just to get to the moon. And if we're going to travel to Mars, it's going to be 8.5 months to get there, and then 8.5 months back. That's quite some time. So if you haven't watched The Martian in a while, maybe that's also a good read for you. This transfer is called a Hohmann transfer. And I'll show you what that looks like. This is an easy find on Wikipedia. And a little bit more, so you can see that there's a delta V here on the starting planet. And that's to eject from the velocities you have in the stable orbit on the planet that you start from, the original planet. And so now you'd be inserted into an elliptical orbit, and then to transfer from the elliptical orbit to now the circular orbit of the planet you're going to, then you'll need another boost in velocity, another increase in velocity in order to stay there. And then to come back, well, you're going to want to slow down, delta V, get back into this elliptical orbit, and then another delta V to slow down, and then into the atmosphere. So let's also just rewind the clock a little bit and take a look at the timing that's involved. So I'm going to share my screen again, and then we'll just go back and take a look at that video, because I backed it up a little bit. Right, you'll notice that the orientation between the two planets has to be just right, because it's one thing to go out to Mars orbit, but it would be nice if Mars was there when you got there. So let's play this through. All right, so here we go. This is just doing a calculation. This is the hard way to do this calculation. Using Kepler's third law is much easier. Or the law of ratios.
How long the spacecraft goes in orbit of its own.
So you'll notice that
Take to get from the Earth. Position of the orbit of Mars.
so that Mars actually had to leave planet Earth by the correct distance in order for us to have our spacecraft actually be there. And that angle is called an opportunity. So we can't just go to Mars whenever we want. Otherwise, Mars is not going to be in the position that we want. So there's our 8.5 months that we came up with earlier. And you can see the planetary alignment has to be just right as well. So during this time, if Mars is leading us by 44 degrees, in the time it takes our space probe to get to Mars's orbit, Mars will actually be there. So our spacecraft executes 180 degrees in its orbit, while Mars, because it's a little bit slower, is going to execute 136 degrees in its orbit. So that means for a successful launch, the angle has to be 44 degrees. And that doesn't happen that often. It only happens every about 2.5 years. So that's the current space race, is that every 2.5 years, we're popping something. Usually we're sending something off to Mars. And now the Chinese are in on it too. So this 44 degrees is called an opportunity.
That alignment is called an opportunity.
Right, we'll just let this run for a second. So when the alignment is right, then you launch. And then that's how you know that your space probe is going to reach Mars orbit when Mars is at the right place. Great, and there's a quiz question like this, so good luck on that quiz question.